deep in the cosmos. Over 8 billion years after the Big Bang, black holes silently shape the universe. From stellar remnants left by stars 20 times the sun's mass, to supermassive giants weighing billions of suns at galaxy centers. These objects bend space, warp time, and challenge our understanding of reality. In 2019, humanity captured the first image of a black hole's shadow, confirming theories Einstein proposed more than a century ago. But what really happens inside a black hole? Can anything survive its pull? Or does time itself stop? Today, we explore 100 relaxing and mind-expanding facts about these cosmic enigmas. Prepare yourselves. We begin. Chapter 1. The Birth and Nature of Black Holes. Close your eyes and imagine a star so large that its blue light shines across space, a giant blazing at more than 20,000 degrees Celsius, glowing hundreds of thousands of times brighter than our sun, its heart alive with the dance of fusion. Hydrogen becoming helium, helium turning into carbon, oxygen, and finally into iron. Every stage of burning marking another chapter in its long life. But like all stories, this one has an ending, because fuel is not infinite, and when the last reserves of energy fade away, the balance between pressure and gravity breaks. The core begins to collapse, and what was once a brilliant beacon slowly approaches its final moment. Science tells us that stars more than 8 times the mass of our sun cannot simply fade into quiet embers. Instead, they explode, releasing everything in one last magnificent outburst. The event we call a supernova, a cosmic farewell that lights up the universe with a beauty mixed with tragedy. It is natural to wonder what happens to a star when it no longer has the power to shine. What remains when the fire has burned through every last atom of fuel? The answer lies in the heart of collapse itself, in the path that leads toward the dark mystery we call a black hole. And as you listen, let yourself drift into the slow rhythm of creation and destruction, light giving way to darkness, energy surrendering to silence. A reminder that even the brightest fire must one day rest, leaving behind something stranger, deeper, and far more powerful than we can see with our eyes. When the final spark fades, the star explodes in a supernova, brighter than 100 billion suns, so powerful that it can be seen across galaxies, even from the surface of Earth. In those moments, the star seems to defy death by shining in a brilliance beyond imagination. Yet this is only the beginning of something more profound. For within the heart of that explosion, the core continues its collapse, shrinking smaller and smaller, density rising past the limits of ordinary matter, until atoms themselves are crushed and space bends under the pressure. What forms is a black hole? A silent shadow born from overwhelming force. Scientists recall the event of 1987, when a supernova lit up the night sky, known as SN 1987A. The clearest example we have observed with human eyes and instruments. Through it, we came to understand how endings and beginnings in the cosmos often exist as one. Imagine a glowing wave of light rushing outwards. And then, as it fades, silence, a quiet so deep that it feels like the universe itself has paused to take a breath. Black holes are not created in peace but in violence, yet their presence afterward is one of stillness, an invisible anchor hidden in the fabric of space. As you think of this picture, allow yourself to float with the thought of energy released and then gone, brightness followed by calm, and recognize how the universe moves in rhythms of expansion and rest, not unlike the rhythm of your own breathing tonight. Not every giant star meets the same fate, for the outcome depends on size. Stars more than 20 to 25 times the mass of our Sun collapse into black holes, while stars between 8 and 20 times the mass of our Sun may collapse into neutron stars instead. Both are dense beyond imagination, but the difference is striking. A neutron star is no larger than a city, yet holds more mass than the Sun, while a black hole hides itself completely, becoming a well in space from which nothing can escape, even light. Scientists describe that if you could take just a spoonful of matter from a black hole, it would weigh billions of tons. Such is the power of compression that defies every sense of scale we know. We may wonder how this compares to our own star, the Sun that gives us warmth and life each day. If the Sun somehow collapsed into a black hole, it would not swallow Earth instantly. Our planet would keep orbiting around the invisible center as if nothing had changed. The difference would be in light, for darkness would reign in place of day. This thought draws us deeper into reflection. What seems eternal in our daily life is not immune to the laws of cosmic change. Everything is bound by the flow of time and energy. Yet in this flow there is a strange comfort, knowing that we are part of the same cycle as stars, bright for a while, then quiet, carried along by forces much greater than ourselves. And so we listen and we drift, guided by the story of stars collapsing into silence. Among the many types of black holes, the most common are stellar black holes, born from the collapse of massive stars. These objects usually hold a few times, or perhaps a few dozen times the mass of our Sun, hidden from direct sight, but revealed through the way they pull on nearby stars and gas. When matter falls toward them, it heats up and glows in X-rays, creating a signal that astronomers can trace across the sky. In the Milky Way alone, there may be tens of millions of stellar black holes, quietly moving with the stars, invisible yet present. Their small size in cosmic terms makes them difficult to find. Yet their numbers remind us that black holes are not rare or distant curiosities, but familiar neighbors in the galactic sea. Imagine drifting in space and knowing that countless of these dark wells surround you, scattered like hidden stones beneath the surface of an endless ocean. The thought may bring a quiet shiver, yet it also carries wonder, for the universe holds far more than what our eyes can see. As you listen tonight, let this image soften into calm. Many black holes scattered across the galaxy, each one a silent witness to the life and death of stars. Far grander in scale are the supermassive black holes, objects so immense that they weigh millions or even billions of times more than the Sun. These titans rest at the centers of galaxies, shaping the stars that form and guiding the structure of their spiral arms. At the heart of our own Milky Way lies Sagittarius, a star, a black hole with the mass of about 4 million suns. Though we cannot see it directly, we know it is there from the way stars orbit with incredible speed around an invisible point. It is natural to wonder if every galaxy shelters such a giant in its core, and many astronomers believe the answer is yes. These black holes may have played a central role in the birth of galaxies themselves. The presence of something so heavy yet unseen reminds us that cosmic order is often held together by forces beyond our senses. Picture the calm center of a storm where everything is drawn inward and held still. That is what a supermassive black hole is for a galaxy. both dangerous and stabilizing, both hidden and essential. As you let this thought sink in, imagine yourself at the quiet center of your own life, watching the motion around you, steady and at rest. Between the stellar black holes and the giants at galactic centers lies a class that is harder to find: the intermediate black holes. These objects are thought to be formed when several smaller black holes merge together, or when a massive star cluster collapses into a single core. Their size places them in the middle, larger than any single star could produce, yet far smaller than the monsters at galactic hearts. Astronomers long searched for signs of them, and in the year 2020, a discovery offered proof. The instruments known as LIGO detected the waves of two black holes merging to create one with a mass about 142 times that of the Sun. This was the first clear evidence of an intermediate black hole, still so rare and mysterious that we may have seen only the beginning of their story. Reflecting on this discovery, we feel as if we have just touched the tip of a vast iceberg, most of it still hidden below the surface, the unknown stretching outward in silence. These black holes remind us how much remains unseen in the universe, and how even in the age of science we stand at the edge of wonder, knowing that mysteries wait patiently for us to find them, like gentle shadows drifting far away, quiet yet immense. In the year 1916, while the world was shaken by the battles of the First World War, a German physicist named Karl Schwarzschild was serving at the front. Surrounded by the noise of shells and the weight of conflict, he turned his attention to the new equations published by Albert Einstein. From within the trenches, he solved them in a way no one had before. What he found was a description of space bending so strongly that not even light could escape. He called it the Schwarzschild radius, a mathematical boundary that marks the edge of a black hole, though he himself did not live long to see how powerful this idea would become. His work stood as the first exact formula of what we now call a black hole. In the midst of destruction and war, he had drawn the invisible frontier of the cosmos, a place where time and space fold into silence. Thinking of this moment gives a strange sense of wonder. Between fire and smoke, a single human mind reached across the universe and touched an idea that would outlive centuries. Between chaos and fear, he outlined the border of an abyss, as if to remind us that even in darkness, discovery can be born. And so the story of black holes begins not with telescopes or machines, but with a man writing on paper under the weight of history, showing us that thought itself can light a path into the most hidden corners of the cosmos. Einstein had opened the door with his theory of general relativity, a vision of space and time woven together. But even he was cautious about the extreme predictions that came from his own work. He called black holes strange solutions, mathematical curiosities that seemed too unreal to exist in nature. His hesitation reminds us that even great minds hesitate before mysteries. For to imagine a place where light is trapped and time bends infinitely was almost too much for science in the early 20th century. Still, the equations remained, quietly insisting on their truth, waiting for decades until technology and observation could catch up. Only in the middle of the 20th century did astronomers begin to accept that black holes might not just be symbols in a theory, but real objects in the sky. This long delay shows us how human understanding often takes time to grow, and it leads us to reflect. If even Einstein himself doubted black holes, how certain can we be of anything? Perhaps the lesson is that mystery and uncertainty are not failures, but companions on the journey of discovery. As you listen now, let the thought of patience and slow unfolding rest in you. Knowledge blooms not all at once, but step by step, as if the universe wants us to learn in rhythm with its own vast breath. The turning point came with the stars. In the year 1964, astronomers studying X-ray signals discovered a source in the constellation of Cygnus. They called it Cygnus X1, and soon realized that the strange light could only be explained if a black hole was pulling matter from a nearby star. For the first time, humanity had indirect evidence that black holes were not only possible but real. The discovery was made through international cooperation, with teams sharing data across borders, proving that the mysteries of the sky call us to work together. Among those who followed this research was Stephen Hawking, who once made a famous bet with a colleague that Cygnus X1 was not a black hole. Yet as the evidence grew stronger and stronger, he conceded, admitting that the hidden well of gravity was indeed there. This story captures the heart of science, bold skepticism giving way to humble acceptance when facts are undeniable. From an idea once dismissed as fantasy, we had found a real shadow in the heavens. And in that moment, black holes crossed from imagination into reality. As you rest tonight, let yourself linger on this truth, that through doubt and persistence, humanity can trace even the darkest outlines of the universe. And you may ask yourself, what turns strange ideas into scientific certainty? Perhaps the answer lies in patience, evidence, and the willingness to see beyond what feels possible. At the edge of every black hole lies a boundary so strange that even light cannot cross it. This boundary is called the event horizon. It marks the invisible surface beyond which nothing can return. The event horizon is not a solid wall, but a threshold, a point where escape velocity equals the speed of light. And because nothing can travel faster than light, this frontier is absolute. Scientists describe its size through the Schwarzschild radius, a value that depends only on the mass of the black hole. A small black hole a few times heavier than the sun may have an event horizon only a few kilometers wide, while a giant black hole at the center of a galaxy can have one that stretches across billions of kilometers. Though invisible, the horizon acts like the ultimate border of space itself. Imagine it as a silent line drawn in the fabric of the universe, a place where motion flows in only one direction, inward, never outward. It feels like a cosmic shoreline, but one where no wave can return. It is natural to ask what would happen if an astronaut touched this horizon. Would time stop? Would they vanish? Or would they simply cross into a place we cannot see? The mystery lingers, as vast and quiet as the night sky. From far away, the event horizon appears like a stage for illusions. Light bends as it struggles to escape. Signals stretch and fade, and to an outside observer, an object falling toward the horizon seems to slow down, appearing to freeze just at the edge. In truth, the object continues on, but its light grows weaker and redder until it disappears. Radio signals, too, will fade, thinning like a whisper carried away by endless distance. This strange effect comes from gravity pulling on time itself, slowing the clock of the falling traveler. So while the astronaut feels their descent as natural and unstoppable, those watching from safety would see them locked forever at the border, caught in a picture that never changes. From this distance, the scene feels eerie, as though the universe has created an eternal mirage, something trapped at the rim of darkness yet never crossing. We might say it looks like the cosmos is holding its breath, watching an image linger that should have already passed. The event horizon is more than a frontier. It is a place where perception itself begins to break, where time divides into two versions, one outside and one within. both real yet never touching. For decades, the event horizon remained a concept in equations, unseen and unproven. Then, in 2019, astronomers unveiled the first direct image of a black hole, the famous picture of the giant called M87 star, more than 50 million light-years away. In that image, we do not see the black hole itself. We see its shadow, the dark circle where the event horizon blocks light, surrounded by a glowing ring of matter heated to millions of degrees, gas and dust spiraling faster than any storm on Earth, creating light so fierce that it shines across galaxies. That bright halo outlines the invisible border, making it visible for the first time. To the eye, it resembles a cosmic eclipse, a permanent dark sun surrounded by a fiery crown, a solar eclipse frozen for eternity. This picture changed our understanding, turning theory into vision, turning imagination into proof. Yet it raises its own question. Are we seeing the black hole itself, or only the shadow it leaves on the universe? Perhaps what we witness is not the object, but its absence, the silent mark of a place where light itself is taken. And in that silence lies both beauty and fear. At the very center of a black hole lies the singularity, a point where density becomes infinite and our familiar laws of physics collapse. In this place, space and time themselves end. Gravity is so extreme that all paths lead inward, matter compressed beyond comprehension. It is the ultimate limit of what we can understand. Some scientists describe it as the hidden heart of the black hole, a place where known physics fails, a mysterious core wrapped in shadow. No light can escape, no signal returns, and we can only model what happens with equations and imagination. The singularity may represent more than destruction. It may be a clue to new physics, a boundary between what we know and what we have yet to discover. Perhaps it is not a point, but a window into a deeper theory, a structure waiting to be unveiled. And we can ask, could the singularity be simply a sign that our understanding of nature is incomplete? A placeholder for knowledge we have not yet grasped? As you drift through this thought, picture the center of the black hole not as a threat, but as a silent teacher, challenging our certainty and inviting us to wonder, reminding us that even the strongest laws have limits, and that curiosity can travel to the darkest corners of the universe, beyond light and time. Some theories propose that the singularity might not be a true point of infinite density, but instead replaced by a quantum structure. In models that combine gravity with quantum mechanics, the classical singularity is smoothed out, replaced with a complex geometry at the smallest scales. String theory and quantum gravity suggest that space itself may be woven differently near the core, but so far no direct observation confirms these ideas. Simulations on computers offer glimpses, yet the truth remains hidden. The deeper we look, the more fragile our certainty seems. Each layer of knowledge reminds us of the vast unknown, and the closer we get to the heart of a black hole, the more we feel the fragility of human understanding, like sand slipping through fingers. Yet we continue to explore, to calculate, to imagine, for the singularity is both a challenge and a call to push the limits of what science can reach. As you listen tonight, consider how the universe allows us to approach its extremes without ever fully grasping them, and let the thought of hidden knowledge settle gently, like quiet shadows at the edge of sight. Physicists have long sought to model the collapse of a star into a singularity using supercomputers. These simulations recreate the extreme pressures and densities at the core of dying stars, helping us estimate how matter behaves when crushed beyond the scale of atoms. Imagining the interior of a black hole is like trying to picture what lies inside a sealed box that cannot be opened. Yet even without direct access, we can explore its effects on the universe, predict the behavior of light and matter near it, and understand the flow of energy and gravity that surrounds it. These models are a testament to human ingenuity, a bridge from theory to insight, and they also raise questions. Could the singularity be the key to unlocking new physics, a hidden doorway beyond Einstein and quantum theory? The black hole challenges us to rethink space, time, and reality itself. And as you imagine this silent core, dense and unknowable, let it drift into your thoughts, a reminder that the universe is vast, full of secrets, and patient, waiting for curiosity and imagination to meet it. Around many black holes lies an accretion disk, matter spiraling inward in a cosmic whirlpool, heated to millions of degrees as friction and gravity squeeze it into light. The disk glows in X-rays and gamma rays, making the black hole visible indirectly. Without it, the dark center would remain completely hidden. The disk is a swirl of energy and danger, a spinning halo of fire surrounding an invisible abyss, its motion hypnotic and fierce. Matter races around the black hole at enormous speeds, each particle following the curve of space-time. The accretion disk is not just a source of light, but also a tool, allowing astronomers to detect and measure black holes across the universe. Imagine a giant vortex of fire wrapping around a shadow, a deadly dance where energy is released with every orbit. It is natural to ask what keeps this infernal circle shining so brightly, why the light does not fade even as matter is pulled inward. The answer lies in physics, in the conversion of gravitational potential energy into radiation, a process far more efficient than nuclear fusion. A cosmic furnace fueled by the very pull of gravity. The energy released by accretion disks is staggering, more efficient than the fusion reactions powering stars. Up to 40% of a particle's mass can be converted into pure energy. A single gram of matter spiraling inward produces more energy than an entire nuclear bomb. This shows that black holes are not merely sinks, but engines, turning destruction into radiant light. The power they release illuminates galaxies, drives jets, and heats the interstellar medium. They are both devourers and creators, a paradox of the cosmos. The disks act as cosmic lighthouses, and their brilliance is a reminder of the scale of forces in the universe. The energy radiating from these disks dwarfs any human experience. Yet in this overwhelming power there is beauty and symmetry. The laws of physics elegantly converting matter into light. And as you picture this flow of energy, imagine the disk spinning silently, its light a constant in the darkness, a pulse that guides our understanding of the invisible heart it surrounds, a cosmic fire we can witness from billions of light years away. Jets often emerge from the poles of black holes, streams of charged particles launched at nearly the speed of light, extending thousands of light years into space, visible in radio waves and other wavelengths. These jets are powered by the same energy that fuels the accretion disk, yet focused into narrow, almost unnatural beams, like cosmic lighthouses shining across intergalactic darkness. They carry away angular momentum, allowing more matter to fall inward, and in doing so, they shape galaxies and cosmic structure. Their scale is almost unimaginable, stretching across distances larger than entire star systems. Yet their origin lies in the invisible, spinning core, a reminder that even unseen objects can influence the universe profoundly. It is natural to wonder why black holes can both swallow matter and simultaneously launch it across space. The process is still a frontier of astrophysics, a place where observation meets theory, and where every discovery opens new questions. As you picture these jets, imagine light and matter arcing outward like a cosmic signal, a bridge from darkness to the observable universe, a reminder that black holes are not mere voids, but active participants in the story of space. The gravity of a black hole is unlike anything we experience. Near the event horizon, the force is so strong that the escape velocity equals the speed of light. Nothing can resist. Even light is trapped. The pull is concentrated into a region so small that it is hard to imagine. A black hole 10 times the mass of the Sun may have a radius of only a few dozen kilometers. Compressing the Sun itself into the size of a city, it is a pit without bottom, a well that swallows everything, from matter to imagination. Tossing even a grain of sand into such a void would send it on a one-way journey into darkness. The force bends space itself, warping paths and slowing clocks. It is a place where Newtonian intuition fails, a place where the mind must stretch to grasp reality. Thinking of this pull can evoke awe and unease. The immense gravity is not just a physical effect, but a philosophical reminder. The universe can compress both matter and certainty into a single point, and in this compression we glimpse the limits of our understanding. What happens when we cross that threshold is a question for both physics and imagination. And as you reflect on this gravity, allow yourself to drift, feeling the pull without fear, carried by thought into the silent depths. Objects falling into a black hole experience spaghettification, stretched into long, thin strands by tidal forces. The difference in gravity between the head and feet of a falling object becomes enormous, pulling it into a shape resembling an endlessly stretched noodle. The effect is extreme near small black holes, but less noticeable near supermassive ones. Yet the principle is the same. Matter is elongated by differences in gravitational pull. Every particle follows space-time, drawn along curves dictated by the mass at the center. The image of spaghettification captures both danger and strangeness. It is a visual metaphor for the limits of physical law. We may ask if all matter, regardless of composition, must undergo the same fate when approaching the event horizon. And the answer seems yes, for gravity is impartial, and its pull universal. Imagining this slow stretching can feel hypnotic, a reminder of the strange, elegant, and sometimes terrifying logic of the universe, a place where size, distance, and scale behave in ways our senses cannot fully grasp. Comparing a black hole to Earth or the Sun makes its extremes clearer. A black hole with 10 times the Sun's mass, but only a few dozen kilometers wide, concentrates mass into an unimaginable density. The Sun compressed into a city is almost incomprehensible. And yet gravity is not only local, but absolute, warping space and time around it, pulling on matter and light, bending trajectories, and capturing imagination itself. It is a reminder that black holes do not merely affect matter, but also our understanding. Their presence challenges our assumptions. Their scale dwarfs familiar objects, and they make us reflect on the smallness of human perception. The force of gravity is the sculptor of light and time. And as you picture this extreme compression, let it drift into your mind. A silent, powerful lesson in the limits of scale and the persistence of natural law. A reminder that in the universe, gravity can not only move mountains, but also erase worlds from sight. Near a black hole, time itself stretches and slows, a consequence of Einstein's theory of relativity. Clocks close to the event horizon tick more slowly than those far away, a phenomenon called time dilation. 1 hour for an observer near the black hole could equal years for someone at a safe distance. The effect is not science fiction, but a real physical outcome of extreme gravity. In thought, we can imagine standing at the rim of a black hole and watching the universe age in fast motion, while our own moments stretch into eternity. This bending of time invites questions. Could time travel ever exist? If we simply approach such a gravitational well, the universe offers the closest analog to time machines through the warping of space-time. And yet, the effect is subtle in smaller black holes and extreme near the supermassive giants at galactic centers. It is a poetic and literal reminder that time is not absolute, but relative to space and mass, letting us reflect on the impermanence of moments and the elasticity of experience itself. The mind drifts along with this stretching, imagining 1 instant becoming 1,000 outside, and 1 second feeling infinite within. Movies, like Interstellar, illustrate time dilation, showing a crew spending hours near a black hole while decades pass on distant planets. The depiction is scientifically guided by Nobel laureate Kip Thorne, ensuring realism in the bending of time. These fictional images allow us to glimpse what extreme gravity does to reality, and to think about time as a flexible medium, not a rigid constant. 2 worlds moving side by side, yet experiencing duration differently. 1 minute here may equal a lifetime there. The parallelism is both fascinating and humbling. It reminds us that our usual experience of time is local, and in the cosmos, time flows differently depending on where we stand. Considering this in the calm of night lets the mind expand, imagining simultaneous experiences stretching across space, a quiet meditation on relativity, on perspective, and on the intimate connection between gravity and the passage of moments. Even in everyday life, time dilation matters. For GPS satellites orbiting Earth, clocks tick slightly faster than those on the surface. Engineers must correct for this tiny difference. A few milliseconds per day would accumulate errors in navigation if unaccounted for. The principle proves that time is intertwined with space and gravity, not just a theoretical curiosity. Though small, the effect is measurable, a testament that Einstein's insights into the relativity of time hold true everywhere, not only in thought experiments, near black holes or in laboratories, but also in our technology. These differences, though minute compared to extreme black holes, remind us that time is never absolute, and that even the ordinary is shaped by the universe's geometry. We might wonder, if time bends and stretches with mass and gravity, is any moment universal? Or is every instant a reflection of the place where it occurs? And as you reflect, let yourself relax into the rhythm of relative time, imagining the universe as a gentle, malleable river carrying experience along its curved paths. From the outside, it appears that matter vanishes when crossing the event horizon, swallowed by darkness without return. Yet within the black hole, the matter still exists, compressed into the singularity, hidden from view, like a drop falling into an ocean. It merges and disappears to the eye, but remains part of the whole. The disappearance is only apparent, a visual illusion caused by extreme gravity. Light cannot escape to inform observers of the true fate of the matter, and yet it is there, part of the black hole's mass and structure. This duality is one of the strangest properties of black holes. Matter gone, yet not gone. Invisible, yet existing. The metaphor of water slipping into the sea captures the essence, the black hole as container of secrets, of energy and mass folded beyond perception. We might ask if information, The details of the object itself can also vanish, and physics wrestles with this question, trying to reconcile disappearance with the unbreakable laws of nature. The so-called information paradox asks if data swallowed by black holes is lost forever. Stephen Hawking initially argued that information could vanish completely, challenging fundamental principles of physics. Later, he revised his view, proposing that subtle quantum effects could allow information to escape. The paradox remains one of the deepest questions in modern science, a test of how gravity, quantum mechanics, and the nature of reality coexist. The mystery transforms black holes into a proving ground for human intellect, where theoretical exploration meets the limits of observation. Pondering this invites awe, for in contemplating disappearance and persistence, we confront both the universe and the boundaries of knowledge. Black holes test not only matter and light, but also imagination and reason. And as you consider these questions tonight, allow the paradox to drift softly, a silent challenge at the edge of thought, a reminder that some mysteries are both unreachable and beautiful. Hawking radiation reveals another strange property. Black holes can slowly evaporate, matter and energy returning as faint radiation over immense timescales. Small black holes could vanish within a time far shorter than the age of the universe, while massive ones persist longer. This radiation is like the final embers of a dying fire, a subtle glow emerging from the darkness, offering a path for matter and energy to escape after all. The image of a black hole gradually shrinking and disappearing evokes both melancholy and wonder. For what seemed eternal is finite. What was hidden becomes faintly visible. We can imagine the universe witnessing the final whisper of a black hole, fading into quiet. And naturally we ask, could all black holes one day vanish completely, leaving nothing but traces? The ultimate silence of the cosmos. And as you drift towards sleep tonight, let the thought of this slow vanishing rest in your mind, a gentle meditation on impermanence, the cycles of energy, and the quiet rhythm of the universe itself. If you've enjoyed drifting through the mysteries of black holes tonight, please like and subscribe to Cosmic Sleep Science to join us on more gentle journeys through the universe's wonders.